Okay, I think you understand. Now overdamped response, critically damped response, underdamped response, right? Now in the underdamped response, just now we just observed here. Exponentially decaying. Decreased amplitude of oscillations. Now students, first you just concentrate here. Exponentially decaying and damped frequency of oscillations. Now let us say this is at t1 seconds, this is the error E1, the deviation of output from the reference level. At t2 seconds, this is the error E2, like that E3. If you observe, then what happened now? Now this error is decreasing, and the response will reach to the final value with error of 0. Now when error equal to 0, now that output is called as, when error is 0, or minimum, and that response is called as accurate response, which is produced by, that accurate response is, you can get here, that type of accurate response you can get in overdamped or critically damped. No, even it is stable, but error analysis if you consent, now this is an accurate response. That's why the underdamped response, which is a preferable response. Now that is the reason why the underdamped response is preferable. What is underdamped response? The underdamped response C of t, which is equal to 1 minus some constant into e power minus zeta omega n into t sine of omega dt plus theta. What is theta? I will tell you. Okay, just a minute. Theta. So now this is the unit step response of a second order closed loop control system in the underdamped, 1 by zeta omega n, and you know omega d, the damped frequency of oscillations, omega n into square root of omega d, which is equal to omega n into square root of 1 minus delta square radians per second, and theta value we will see. Okay, so I want theta, right? Now this is the unit step response. This is the unit step response of a second order system. Unit step response of the second order system, in which case, under damped case, damping factor zeta less than 1 and greater than 0, right? Now you want theta, right? Sir, what is theta, sir? How we can find, sir? What is the meaning of that is? Now see here. Now you know the poles location in the underdamped response? Yes. What is the poles location? These are the poles which are complex conjugate. The underdamped response poles are complex conjugate and which lies on left hand side of S plane. The underdamped response poles are complex conjugate which lies on left hand side of S plane. Now this is nothing but minus zeta omega n. Now this is plus j omega d. This is minus j omega d. This is the complex conjugate poles location, which is left hand side. Now this is minus zeta omega n plus j omega d minus j omega d. Now see here. Now this is the negative real axis. This is the positive real axis. This is the positive imaginary axis. This is the negative imaginary axis. You know that. Now from the origin, if I draw a vector line to this complex conjugate pole, now this vector line will make some angle with respect to the negative real axis or not? If I draw a vector line to this complex conjugate pole, now this vector line will make some angle with respect to the negative real axis. Now that angle is called as, that theta is called as angle of inclination. This is not a perpendicular angle. This is some inclined angle. This theta is called as angle of inclination to the complex conjugate pole from the origin with respect to negative real axis. That is the theta. Now what is the definition of theta? Theta is called as angle of inclination. Theta is called as angle of inclination, inclined angle, angle of inclination, inclined angle. Theta is called as angle of inclination to the complex conjugate pole from the origin with respect to negative real axis, inclined angle. Now, with respect to this complex conjugate pole, we'll make a right angle triangle. With respect to complex conjugate pole, we'll make a right angle triangle. Now, this is the angle of inclination theta. Now, you see here. Now, what about this adjacent distance? This adjacent distance is zeta omega n. And what about this side distance? This side distance is directly omega d, damped frequency of oscillation. This is zeta omega n. This is omega d. What is this hypotenuse distance? Now that hypotenuse distance is nothing but square root of omega d square plus zeta square omega n square. Now which is nothing but square root of omega. What is omega d square? Omega d square is nothing but omega n square minus omega n square into zeta square plus zeta square into omega n square. So this is cancelled. Omega n under root is cancelled. This is omega n. So therefore this hypotenuse distance is nothing but omega n, undamped natural frequency of oscillation. What we want? We want angle of inclination theta. Now I want angle of inclination theta. Now I want a tan of angle of inclination. Then if you take a tan of angle of inclination, now side by adjacent, omega d by zeta omega n, which is equal to, what is omega d? Omega n into square root of 1 minus zeta square by zeta omega n. Omega and omega n cancel. So angle of inclination theta, which is nothing but tan inverse square root of 1 minus zeta square by zeta. This is angle of inclination theta. Now what is the cos of angle of inclination? The cos of angle of inclination theta, which is nothing but, the cos of angle of inclination theta is nothing but adjacent by hypotenuse. Adjacent is zeta omega n by hypotenuse is omega n. So the cos of angle of inclination theta is nothing but directly the damping factor zeta. And similarly, the sine of angle of inclination theta is nothing but side by hypotenuse omega d by omega n, which is equal to square root of 1 minus zeta square. This is the angle of inclination theta. Okay. Now what is the role of angle of inclination theta also we will see. First you take this one. Okay. Now this is the omega d plus theta. This theta is called as angle of inclination. Will play the important role in the second order analysis. That also we will see. Okay. So once we will finish the transient response in the first order, now what you are doing next? Time domain specification. Now in the same thing also we will do it here in the second order also. Now we want to find the time domain analysis in the time domain specifications we will see. Okay. Now time domain specifications of a second order closed loop control system. And finally, all the time domain specifications, students, you have to remember, all the time domain specifications you are going to be calculated for which response? This is the response, unit step response of second order system. In which case? Underdamped response. This is the underdamped case. Okay. Now we know the theta value also, so not an issue. Now you know theta. What is theta? Tan inverse square root of 1 minus zeta square by zeta. This is theta, right? Now time domain specification. Let us start with first rise time. Definition is important. So see the definition in this diagram. I will explain the definitions in the diagrams. If you understand this one, it is very easy to understand the definition and parameters also. Okay. Rise time. The time taken by the response to rise from 0 to 100%. The time taken by the response to rise from the time taken by the response to rise from 0 to 100% is called as rise time. The time taken by the response to rise from 0 to 100% is called as rise time. Now this is the first parameter, is called as rise time, TR. Rise time. The time taken by the response to rise from 0 to 100% is called as rise time. So this is the response. Now this response is reaches to 100%, then you can get a time. That time is called as rise time. Where is the response? This is the response. 1 minus k into e power minus zeta omega n into t sine of omega dt plus theta, which is equal to 1 minus 1 0 sine of omega dt plus theta is equal to 0. Now this is, can I write like this? This is sine of omega dt plus theta. Sine n pi is also 0, right? Sine pi, sine 2 pi, sine n pi. Then I just take this is sine phi. So if you compare these two, when this is response is equal to 1, now this time is called as rise time. This time is called as rise time. Therefore, omega tr plus theta is equal to pi. Therefore, now the rise time tr, which is equal to pi minus theta by omega d seconds. This is the rise time tr. The time taken by the response to rise from 0 to 100% is called as rise time. This is the rise time tr. The time taken by the response to rise from 0 to 100% is called as rise time. Okay, this is the first parameter, now which is the time domain specification in the underdamped response. Note down this. Now we'll see the second parameter, peak time. Now this is the second parameter, peak time, TP. What is a peak time? The name itself, peak time, okay? The time taken by the response to reach, its peak value. The time taken by the response to reach its peak value, to reach its maximum value is called as peak time. The time taken by the response to reach its peak value, to reach its maximum value is called as peak time. Now the students, I am asking how to find the peak time, how to find the maximum value of any function. Tell me, how to find the maximum value of any function? Now if you differentiate the response with respect to time, right? Now the maximum value is finding the differentiation. Now this is the response. Now this response, now first you should differentiate this response d by dt of c of t, differentiate the response with respect to time and equal to 0. Now this time is called as peak time. Differentiate the response with respect to time and equal to 0. Now that time is nothing but the peak time. Differentiate the response with respect to time is called as peak time. So if you differentiate this response, same differentiation of 1 is 0. Now this is UV method, differentiation of sine is cos. Now differentiation of exponential, and this is constant. That peak time is nothing but n pi by omega d. You can get this. This is the peak time, n pi by omega d. Now, okay sir, omega d is nothing but the damped frequency of oscillation, where theta is everything is known to you, okay? And one important point I want to say here, this pi is radians, this omega is radians per second. Therefore, this theta you measured in the calculator, the mode is radians, because radians per second, radians cancel, and this is seconds, okay? Don't calculate theta value in terms of degrees, you can get the wrong. This is in terms of radians, okay? Now, what is n? What is n here is, now see here, I can take on numbers here, 1, 2, 3, 4, 5, 6, 7, 8, 9, like this. So if you observe, the time taken by the response to reach its peak means by default n value equal to 1. Second peak means some of the students are saying n equal to, no, wrong. This is not peak. The peak is with respect to steady state value. In underdamped response, in practical response, everything there is a reference level. This is the reference level, am I not? Now with respect to reference level, what is the peak? N equal to 1, 3, 5, 7 and so on. These are peaks. So he is asking peak time means n equal to 1. Sometimes he is asking second peak. This is the first peak. What is the second peak? This is the second peak, student. The second peak is nothing but n equal to 3. Third peak is nothing but n equal to 5. Fourth peak is nothing but n equal to 7, like this. Understand or not? These are the peaks, and these are the values over the steady state level or not? Students, these are the peaks and these are the values over the steady state level. Therefore, these are called as peaks or overshoots. These are the peaks and these are the overshoots. Okay, these are the peaks and these are the overshoots. Next, n equal to 2, 4, 6, 8 and so on. These are the valley points. These are the valley points, or these are the points which is below the steady state level, under the steady state level. This is called as undershoots. Now these are the values over the steady state level is overshoots, under the steady state level is undershoots. Okay, this is peaks, this is valley points, this is overshoots, this is the undershoots. Therefore, nothing is asking peak time n equal to 1, second peak time 3, third peak time 5, fourth peak time 7, like this. This is the peak time. Understand? No, this is the peak time. Now the peak time TP, which is equal to n pi by omega d seconds. Note down this. Okay. Now this is the way you can calculate all the derivations. You can easily access when you have a definition. If you understand the definition, derivation is nothing. Now the third parameter, delay time. Delay time, TD. The time taken by the response, the delay time. The time taken by the response to reach 50%. The time taken by the response to reach 50%. The time taken by the response to reach 50% of the final value. The time taken by the response to reach 50% of the final value is called as delay time. So now this response is reaches to 50%, then you can get a time. Now this time is nothing but delay time, but this is not a derivation part. This is some empirical relation based on the graphical analysis. Now this delay time is approximately 1 plus 0.7 zeta by omega n. This is 1 plus 0.7 zeta by omega n. This is the delay time. So these are the actual time domain specifications. Now rise time, delay time and peak time. Okay. Now these are the delay time. These are the actual time domain specification. In the first order also we will see rise time, peak time, rise time, delay time. Now the same definitions. Okay. Note on this. You just understand in the graph, then automatically the definition and derivations, which is also very simple to you. Okay, but the students are having some doubt. Sir, in first order system you said that rise time definition is different, but here you said the rise time definition is different. Yes, because the response is changing now. But that is also rise time definition. That's why I will give the clarity of here. The time taken by the response to rise from 0% to 100%, which we are used here, is called as rise time. The time taken by the response to rise from 5% to 95% is called as rise time here. The time taken by the response to rise from 10% to 90% is called as rise time. The time taken by the response to rise from 0 to 100% for under damped response, for under damped response. The time taken by the response to rise from 5% to 95% for critically damped response. The time taken by the response to rise from 10% to 95% for over damped response. Now, this is the definition of rise time. But now where you are? We are in which response? Under damped response. That's why we will take 100%. Now, this is the over damped response, or this is also the definition for first order step response. That's why we just in the previous sessions, that is a first order step response. That's why we take the rise time definition is from 10% to 90%. Okay. Now it is clear or not? Yes. And these are the main time domain specifications, and we will see some other time domain specifications also. Take this one. Okay. Now, settling time. You know that. What is settling time? The time taken by the response to reach its final settlement. The time taken by the response to reach its final value, its final settlement is called as settling time. The time taken by the response to reach its final settlement is called as the settling time. You already know that what is the settling time. The settling time, which is equal to 5 time constant, practically 5 into what is the time constant here? 1 by zeta omega n. This is for 0% error. Now the settling time, which is equal to 4 time constant, which is equal to 4 into 1 by zeta omega n. Now this is for 2% error. Now the settling time, which is equal to 5 time constant, which is equal to 5 into 1 by zeta omega n, which is equal to for 5% error. This is the settling time. For any practical response, the settling time will be same, but this is for error 0%, 2%, 5%. These are the settling time. The time taken by the response to reach its final settlement, so is called as the settling time. Okay. So the settling time formulas will be same, but answers will not be same, because the settling time is completely depends upon the time constant. Port location is changing, time constant is changing. In the previous session, first order, now this is second order. Port location is changed, time constant is changed, settling time is also changes. Okay. Now there is one more time domain specification which is available, and which is very important specification. Now that is nothing but peak overshoot. What is that? peak overshoot represented by MP. Peak overshoot represented by MP expressed in terms of percentage. What is peak overshoot? Now I'll give you the definition first you understand. The peak overshoot is the difference between, peak overshoot is the normalized difference between time response peak and steady state peak. Once again I repeat, the peak overshoot which will give the normalized difference between time response peak and steady state peak. If you want to understand this parameter, first sir, what is time response peak, what is steady state peak, which we already finished. Now this response is having two peaks. This is steady state peak. This is steady state peak which is always constant. And this is the first time response peak, second time response peak, third, fourth, fifth, like this. Now this is the time response peak and this is the steady state peak. Okay, these are the time response peaks and this is the steady state peak. Now the student, what he is asking is the difference between, this is the steady state peak and this is the time response peak. First time response peak, second time response peak, third time response peak. The deviation of the time response peak and steady state peak is called as peak overshoot. Now he is saying the deviation of time response peak and steady state peak, but he is mentioned one word, normalizing with respect to steady state value. The normalized difference between time response peak and steady state peak is called as peak overshoot, which is nothing but e power minus delta n pi by square root of 1 minus zeta square. Okay, now sir, how you can get this? You can easily get, you know, C of Tp, substitute here, where there is a T, replace with Tp. C of TSS is 1 by 1, therefore this is peak time, therefore n pi, that's why this will be coming n pi. Sir, what is n? Again same, what I am saying, if n equal to 1, first peak overshoot, n equal to 3, second peak overshoot, n equal to 5, third peak overshoot. But what is important here, now my question is not the parameter, what is the significance of this parameter? What I am saying, the deviation of time response peak and steady state peak, the deviation of time response peak and steady state peak. Students, see here, the deviation of time response peak and steady state peak, the deviation of time response peak and steady state peak, what this deviation will give to you, what this difference will give to you, this difference is nothing but error or not? Yes, the percentage peak overshoot is the best parameter to find the error, to find the system stability with respect to error. Then I will ask one simple question. When percentage peak overshoot is more, what is the meaning of that? When percentage peak overshoot is more means this deviation is more. There is a large deviation. When there is a large deviation, error is more, error is very high. When error is very high, the system becomes less stable, unstable or less stable, because where error is more, then obviously when error is more, unaccurate, then that is obviously unstable system and whose stability is day by day it should be decreased. In the same manner, what is the reverse? Now, if the percentage peak overshoot is less, decreases, deviation is decreases means what? Error is decreases. When error is decreases, what is the meaning of that? System becomes more stable. When error is less, more accurate, more stable. Am I right or not? Now this is the significance of the peak overshoot. Note down. Clear or not? The percentage peak overshoot is the best parameter to decide the system stability with respect to error. The percentage peak overshoot is the best parameter to decide the system stability with respect to error. Okay, don't say stable, unstable. Say this system is more stable because the error is less. This system is less stable because the error is more. Like that, you have to say that. For saying that, the useful parameter to use peak overshoot. Then I will give one small example here also. I just extended this. Now you tell me, when damping factor zeta equal to 0, what is the percentage peak overshoot? When damping factor zeta equal to 0, what is the percentage peak overshoot? Substitute here. When delta equal to 0, e power 0 is 1. So peak overshoot is 100%. When delta equal to 1, 1 minus 1, 0, something by 0, e power minus infinity, peak overshoot is 0%. Now my question is, now here pose is on imaginary axis, system is marginally stable. You know that. But here, when delta equal to 1, pole is completely on the left hand side, system is stable. Now you just see the comparison. When delta is changing from 0 to 1, when delta is changing from 0 to 1 is nothing but delta is increasing. When delta increases, peak overshoot is, see here, see this one. When delta is increases, peak overshoot is, what happened? Peak overshoot is decreases. Now see here, when delta increases, when delta increases, when zeta increases, what happened? When zeta increases, peak overshoot is decreases. When peak overshoot is decreases, what happened? Error is decreases. When error is decreases, system becomes more stable. That is the reason why the marginally stable system will become stable. Our unstable system will become stable. And what is the reverse? When damping factor delta is changing from 1 to 0. When damping factor is changing from delta equal to 1 to 0 means delta is decreases. Now, when zeta is decreases, when zeta decreases, what happens? 0% will become 100%. Peak overshoot is increases. Peak overshoot increases means deviation is increases. When deviation is increases, error is increases. When error is increases, system becomes less stable. That's why the stable system will become unstable or marginally stable. Now this is the relation between peak overshoot and damping factor. What is the relation? The peak overshoot and damping factor is inversely proportional. When damping factor decreases, damping factor increases, peak overshoot is decreases, damping factor decreases, peak overshoot is increases. Once peak overshoot is nothing but the error parameter, you understand. Okay, this is also very important relation between the peak overshoot and damping factor zeta. Okay, note down this. Okay, now these are the time domain specifications and the relations between the time domain specifications. Okay, in the next session we will see what is the time domain specification, what its relations. Okay, when the pose location is given in the second order, now what should be the time domain specification and how it will be related. Okay, we will see in the next session.